So I have two examples to demonstrate some of the basic ideas of quantum circuits. This is a very simple example, but it is important to understand some of the basics. We will go through the matrix multiplication and understand how to read a quantum circuit, right? Again, quantum circuit is nothing. You just put all the quantum gates together and then let it run. So here I want to remind you that, for example, in the C4 space, which how many qubits do we have in C4 space? 2. Yes. So how many bases do we have? 4, right? The standard one, I call it standard one. We did earlier is like 1 0 0 0, right? U2 1 0 1 0 0, U3 0 0 1 0, and U4 0 0 0 1. That is the natural one, right? For example, this one represents 1 1, right? Is that okay? And there's another basis which we talked about earlier is the Bell states. I don't know if you remember what they are. First, it is 5 plus, which is 1 0 0 1, but I need to do square root 2, 1 over square root 2. 5 minus equals to 1 over square root 2, 1 0 0 negative 1. And then psi plus equal to 1 over square root 2, 0 1 1 0. And psi minus equal to 1 over square root 2, 0 1 negative 1 0. Okay, this is just a review. Okay, so we have this basis. Can I have a quantum circuit to convert one basis to another basis? Or it's just think about, can I convert one of this vector to another vector? Remember, when I write it in this way, it is still in the basis of what? When I write this in column form, what basis are we using? The 0 and the standard one, right? Because this means I have one component of 0, 1, and then I have negative one component of 1, 0. Just remember this, right? So how do we do this? Of course, you can find it, but that is not the purpose. I am going to tell you it is given. To do the transformation, it is U exclusive OR, which is the control NOT gate. Remember, it's also exclusive OR gate. Times UH I2, right? So I do not have a consistent, I do not make the symbol consistently. I keep changing the symbol, but I hope that you can follow. Because UH, what else can it be? Hadamard gate, right? It's a unitary gate, Hadamard gate. You can use H also if you want. I2, someone say, is it a 2-qubit identity gate? Is it possible to have 2-qubit identity gates here? Yes, we are talking about C4 space. So is this possible to have that? I mean 2-qubit identity gate? Yeah? Then what is this? No, this whole thing, what is this? (16). But what we are talking about? C4. So can this be 2-qubit identity gate? No. Then what you guess, what's the meaning of 2? The identity gates for the second qubit. That's the only meaning. Right? I know some people complain about this, but the problem is if you read the paper, you look at the websites, they all have different way to label them. But you need to judge, right? It cannot be 4 qubit. We are talking about 2 qubit system, a tensor product with 1 qubit or 2 qubit. It will be 3 qubit already. This is not the right matrix. Make sense? And then this is a 4 qubit times 4 qubit. This is just a matrix multiplication, right? So that's why I want you to think carefully. Yes, I know it's confusing. You can say I'm lazy, but I can say that I do it deliberately because there's no other explanation, almost, unless you come up with one, yeah. I'm going to do that, but the point is, when you look at this, you need to have this in your brain already. This must be one qubit, right? Okay, this is given. It will do the transformation. How does it do? In a matrix, in an operation, right? How does it do? It will do this, right? Maybe this is the output, and then this is the input. Correct? When you do matrix multiplication, you go from right to left. This is a key point. Right to left, unless you invent your own standard. When I give you a matrix, you always multiply matrix to the vector and you get a vector, right? So it's from right to left. But how about a quantum circuit? How do I do this? I'm going to draw it in this way. It goes from where to where? From left to right. It's fine if you don't like that, but unfortunately, this is the standard. That's how you draw the quantum circuit, right? In IBM Q, they go from left to right. Don't complain. That's how you do it. And let's look at which one is the most significant bit based on this drawing. The top or the bottom? The top. And the bottom is the least significant. Why? Because in my matrix, UH is on the left. The Hadamard gate is applied to the first, the most significant bit. I'm not going to say it first or second. The most significant bit, right? The most significant bit is on the left, right? For example, 0, 1. This is MSB. This is LSB. Is that okay? And so based on this, yeah, the most significant bit is on the top. So if you are told that the most significant bit is at the top, of course you need to put H here, which is UH. Then identity gates will be at the bottom. And then we have control node. Which one will be the controlling qubit? The most significant of the least significant. Based on the drawing, it is here, right? From here, actually, you don't know. I need to tell you or you decide from this U exclusive OR, right? But from here, it is this. This is important. It's going to tell me what the matrix are. The matrix is going to be, first I do the exclusive OR 1 0 0 0 0 1 0 0, right? 0 0 0 1 0 0 1 0. This is the exclusive OR. Yeah. And I write the 1 first because this is the equation I'm doing. I do not write HI first. I write this first because I'm doing matrix multiplication. Okay? Yeah.
So circuit based on
yeah. I draw it based on these two equations. This equation. I mean this expression or this equation. Right? V in. How I got that? We have V in. Which operation apply to V in first? I mean not V, psi in. Which operation apply to psi in first? The tensor product of H and I, right? And H applies to the most significant bit, I applies to the least significant bit because of the ordering. I don't have I tensor product H. I have H tensor product I. Question? Yes. Yes. We have had this convention since the beginning, right? When we deal with, for example, the Hadamard gate, we have n Hadamard gate. The first one apply to the first zero, right? Second one apply to the second zero. Same here. Matrix is from right to left. Circle is from left to right. I think we have the same direction. Still confusing? Which part?
Yeah, I think maybe
No, what do you mean by tensor? This is already a tensor product. Or you mean matrix form? Matrix form? You don't need matrix form. You don't see that from matrix form. From here, left one is MSB, right one is LSB. That is the definition in this class. Because this is on the left, so the left one will go to the left, the right will go to the right, again by convention. That is how you write the form. This one has to go to the leftmost one has to go to the leftmost one, the rightmost one go to the rightmost one. You need to follow this. It's a rule. Okay, otherwise you say you want to put I2 to this, UH to this, then it's your own rule. That's okay. You can do that, but it's going to be very messy. But the rule in the community is follow the order. Right? There's no reason why we want to swap it.
there's just a rule there in math behind it. So if I expect that if I write that equation in format, that is not going to help me in figuring out which bit goes to discovery.
It won't, because in your matrix format, you are going to determine what is the meaning of each of these already. We can take a look later if you want to see the matrix format, right? But if you guys all agree this rule, then let's continue. This is the control knot, right? Then how about the next one? Hadamard gate, 1, 1, 1, negative 1, tensor product, 1, 0, 0, 1. Is this okay? So what is this? 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1 over square root 2, and then 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, negative 1, 0, 0, negative 1. Can you follow? If you cannot follow, you won't pass the midterm. How do I do this tensor product? Yeah. Right. So he's telling us how to do it, right? This 1, you just put the whole matrix next to 1, then 1 times this whole thing, give me this block. This 1, give me this block. This 1, give me this block. Then this one is negative 1 times the whole thing, so that's why I have negative 1, 0, 0, negative 1. Okay. And what is this? Just do a regular tensor matrix multiplication. Row times column. If you're not familiar with matrix multiplication, make sure you know that, right? We are going to test in the midterm, right? And you see, the 1 is here. So basically, I'm copying the first row, right? The second one, only the second is 1. So I'm going to copy the second row. The third one, it is the fourth one. So I'm going to get the fourth row here, right? Because this is, last one is 1, right? When I do multiplication, I only have this has effect. Okay? And then finally, we have this one. This is the matrix for the whole circuit. Every circuit, in principle, you can make it into one single matrix. It's just the multiplication of many matrices. Okay? So let's look at an example, right? Again, I run out of space. For example, what happens if I apply to (1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, negative 1, 1, 0, negative 1, 0. Apply this, for example, let's say to U2, which is 0, 1, 0, 0. This is U2. What do you get? What is the first element when you apply to U2? 0. Why? Because there's no overlap between 0 and 1, right? You do this row, multiply this column, you get 0. How about for the second element? What do you get? 1, right? Because the second one overlap. How about the third one? Also 1. How about the last one? 0. Thank you. Which vector is this? Psi plus, right? So just show that, yeah, it does convert a basis vector to the vector in another basis. But still, we are representing it in the standard basis, the 0, 1 basis. Okay? I'm not able to answer the question you asked. Maybe we can play with that later. But the main point here is that you really need to be able to follow or you cannot pass the midterm, right? We are doing, circuit is a big part of the midterm, although I teach it now. But you have all the basics, right? So again, in equation, you go from right to left because you're doing matrix multiplication. A matrix multiply a vector becomes a vector. So you go from right to left. The first thing you see is UH tensor product I2. The second one you see is U exclusive OR. In circuits, convention, we go from left to right. So that's why you need to draw the gate it encounters first on the left, and then the gate it encounters the last on the right. And one more important thing is realize where is the MSB and LSB, how you draw the circuit. The result is the same, but it needs to be consistent. And that is the problem with IBM Q. So in IBM Q, they swap it. They do this. They always have the lowest, the one at the bottom as the MSB, the one on the top as the LSB. Okay? So how should I draw the circuit now based on this? Just swap it. Yeah. It was H on top. Now I'm going to put H at the bottom and then I on top. And how about the control knot? Flip it also. The controlling qubit still is the MSB being the controlling qubit. But we just draw it at the bottom. And that's it. And we still have the same equation, right? Same equation. You just need to arrange it well. Now, this scheme, the scheme we have talking about is called the so-called little endian. That when you write this vector, the one on the right is the smallest least significant. There are some coding scheme that the one on the left is the least significant. That's called big endian. Okay, but we are not going to study here. Okay, so let's just practice one more time. What if we apply this to the same equation? I mean, I should say same matrix. Okay. So remember, you flip the most significant bits and least significant bits. You are not going to change the matrix. It's just the drawing becomes different. But you need to know that when you read it, the bottom one is the most significant bit. This is U1. What do we get? Okay, he said 1001. Let's see. Yeah, the first one is 1. So maybe I wrote it wrong. Oh, there should be no 1 at the end. Thank you. Yes, exactly, because this is the U, right? So 1, 0, 0, 1, okay, which is the psi plus state. Right? Again, here just to show that we do, just give 2 examples, right? So this is very simple, actually. Should be psi plus. Oh, the phi plus, okay, sorry. You're right. Psi plus. Let's see. Okay, yeah. So here is an example, the IBM Q. Do you see it is the same as the circuit I just drawn? I don't have the I because I don't need to. I means just identity, right? So, but sometimes you add it so you can align the gate. Here you will align automatically because you have a C0 gate here, so it's not going to shift. If it's otherwise, it will go there, right? And this is the matrix. So what is the input here? 0, 0, but which U are we doing? It is 0, 0. What is 0, 0, the input? The input, in column form, I should say. You're right. This is 0, 0 by default 0, 0. So how do we write it in column form? 1, 0, 0, 0. This is input, right? And this is actually U1. I think this is the one I did earlier. Okay? And we already showed that it is going to be phi plus, right? So it becomes 1001. And what does it mean? 1 over square root 2. Actually, there's a 1 over square root 2. So I think I missed 1 over square root 2 here, because I have a 1 over square root 2 in the gate, right? So the nature doesn't lie. Eventually, it will just be normalized, okay? Do I miss something here? Yeah, this is okay. This is equal to what? In the bracket form, what is that? What are the basis states? 0, 0 plus 1, 1. Okay? And we do the measurement. Indeed, we get 0, 0, and 1, 1, which are non-zero. 1, 0, and 0, they are 0. And how do we do a measurement in IBM Q? I think you already done assignment 2, some of you, right? But basically, you add the measurement, and we have 2 classical qubits to store the information, 2 classical bits to store the measurement result. By default, the 0th qubit will go to the 0th classical bit. The qubit 1 will go to the classical bit 1. So this is the most significant bits, right? So as a result, it will be also the most significant bit in the output. This is the most significant bits. This is the least significant bits of the classical qubit. And I store the most significant bits of the qubit in measurement results into the most significant bits of the classical register. Okay, we just do it accordingly. Yeah. No, this is just a drawing. I think they just do this as a background. Yeah. It just measure is done here. Just one, nothing special.
Yes, as reading.
Yeah. For all nines, they're ideal, assumed to be ideal. Nothing happened. Is that okay? Let's try one more. How about this one? What is my input here? Maybe a little bit confusing, right? Maybe, oh, that's not the circuit I want, but it is. This is the circuits that we have. Make sense? Is it the same circuit? It's the same, right? Then what's the only difference? The NOT gate. So if this is 0, 0, right? So I need you to be able to trace this. This is 0, 0. What is this? At this, oh no, this is not good. Should be before, yeah. So I did not draw a good circuit. I want to ask this, what is this at this stage? What is this? 0, 1. Do you agree? Because the top is the least significant bit. This is LSB, LSB, MS. This is MSB. Is that okay? So basically, this circuit is that still I'm using the same circuit, but equivalently, what I'm inputting is 0, 1. Okay? So what I need to find is 1 over square root 2, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, negative 1, 1, 0, negative 1, 0. This is the matrix of the whole circuit, and it is applied to 0, 1, 0, 0, because this is saying that I have 1 unit of 0, 1. If you don't like that, you can say, let me do a NOT gate first. I apply to 0, 0, right? But I don't want to waste the time. I just directly apply 0, 1 to that because I see that already. So the result is 0, 1, 1, 0, which is psi plus. Or no. I think I'm right this time, right? Which is 1 over square root 0, 1 plus 1, 0. And what do you get in the measurement? 0, 1, you have so much chance. 1, 0, you have so much chance, which is correct. Yeah.
So the exam we're expecting us to research for this was equation for
No, you need to know everything. Yeah.
So why don't we try this? So we had the expression starting to this slide, and the only thing we have added now is a NOT gate. So I guess by extension, I would say for to the equation that you add two slides ago, you just add a NOT gate to the rightmost side. Of that
Yeah.
equation.
Yeah. Is it enough just a NOT gate? He's saying that what if we try this, right? It's also a good exercise, right? Okay, he's not happy with that we do 0, 1. He wants to go from basics. So he has this C0 gate, which is exclusive OR. And then Hadamard gate, tensor product I. And then he wants to add another NOT gate. Let me just call it U0, right? and then apply this to 0, 0. Is this okay? Any problem with this? Maybe you don't see it here, but once you write in a matrix form, you run into a big problem. What problem is that?
Oh, you have a matrix. First one is a matrix, third one is a matrix, the one in the middle is.
Yeah, matrix.
So matrix times matrix times matrix.
Then how about what's the dimension of this matrix? Huh? What's the dimension of this matrix? 4 by 4. What's the dimension of this matrix? What's the dimension of this matrix? 2 by 2. So is this right? What do you need to do? Yes. So what you need to do is what? But U0 is applied to which qubit? LSB. So you should put on the left or right? Huh? MSB is on the left or right? Yes. So what would be the final expression? Excellent. Yeah, so thanks to him, everyone need to be very careful about this. Okay? And you can verify, right? Let's verify. You're making my progress very slow, but it's good. What is NOT gate? Yeah, this is what? 0, 1, 0, 0, 1, 1, 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, right? And if I apply this to 1, 0, 0, 0, right? What do you get? Huh? Which is 0, 0 here, right? You apply it to here, what do you get? 0? Huh? 0, 1, 0, 0. What is this? Huh? Yeah, U2, 0, 1, right? Is this what we want? Correct, right? What I'm talking about is this term. Yeah, that's right. If you don't go home to play with it, not tensor product I, you won't get this. Is that okay?
Instead of using identity in both of them, we could just use the armor gate tensor product, not gate.
Oh, yeah. You're right. Exactly. Yeah, he said that. Why don't we just do Hadamard gate tensor product to NOT gate? Exactly. That is basically have a very important implication. Just because they are not entangled, this gate, right? You can shuffle them. I mean, you can combine them in any way. You're right. Because in principle, this is like the first cube, the least significant bits go through NOT gate and then identity gates. Then you finish this multiplication first. And then this is second qubit, the most significant bits go through identity gates and then Hadamard gate. You finish this operation first. And then you do tensor product in the higher space. That is another explanation. And or just based on this circuit, isn't that this is tensor product of Hadamard gate and the NOT gate, right? And this is a very good way for you to check your result, right? If you go through all these different directions, you still get the same results. You are very confident that you are right. Okay? Yeah, so this thing is something you need to think, right? Like what you guys have been asking, challenging. By doing that, you really understand, right? Do not just do the math. Keep thinking from different directions.